fundamental theorem of calculus. There are two parts. Today we are learning one of those two parts, and then on Monday we will learn the second part. The fundamental theorem of calculus is essentially the connection of all things calculus in terms of integrating and derivatives. So the two parts are used to evaluate functions. The first part of the fundamental theorem of calculus says that if f is a function on a continuous interval ab, then the function f of x equals the integral from a to x of f of t dt has a derivative at every point in x on that interval. And what that means is that the derivative of capital F of x equals f of x. The derivative of the capital F of x equals f of x. That's part one. That's actually what we're doing on Monday. So the way the fundamental theorem of calculus is taught is we typically start with part two. And we relate it to rates in and rates out. So we're going to relate it to rates in and rates out. Part two of the fundamental theorem of calculus actually has a second name. Sometimes we call part two of the fundamental theorem of calculus the net change theorem. Sometimes it is called the net change or the total change theorem. And what it says is that the definite integral of a rate of change is the net change in the original function. So the definite integral of a rate of change is the net change in the original function. So if you integrate a derivative, you get back the original. So integration and derivatives are inverses of each other. So if you integrate a derivative, you get the original. The net change theorem can be rewritten a little bit differently. Still at the bottom, I think. Yeah, stay at the bottom. Just use that empty space above, like total change equals initial amount plus change in amount from A to B. Sorry. So yeah, this is the statement I put at the bottom. F of B represents total change. F of A is the initial amount. And the integral represents the net change. This theorem is what we're focusing on today. take a minute, and I typed all these steps out for you on the next page in your note packet, but I want you to read through steps 1, 2, and 3. So just take a minute and read through 1, 2, and 3. Okay? So essentially what we are doing is evaluating our integrals, but now we're talking about them in terms of change from point A to point B. So the fundamental theorem of calculus, as we're going to look at it to start, first how we can apply it. So when we look at these next 3 examples, they're very similar to what we've been doing with our integrals. We have a definite integral. We use our power rule. So the integral from -2 to 1 of x cubed dx becomes 1/4 x to the 4th evaluated from 1 to -2. So technically that 1 is like my f of b. That 2 is like my f of a. And I find the area under the curve. Now, how we're expanding upon this is that we're going to maybe be given f of a and an integral, but we need to find f of b. So we're going to be taking this concept and idea and altering it. So right now, this answer here simply represents f of b minus f of a, which is 1/4 minus 1/4 times -2 to the 4th. So you get 1/4 on -2 to the 4th becomes a positive 16/4, but it's still a minus, so it's minus 16/4. So we get -15/4. So that represents the area under that curve, or the value of the integral at the end. So for what we've been doing, that value represents the change. Now we're going to talk about the net change from the beginning to the end. So let's just look at 2 more examples where we're just talking about the integral, which represents that net change, but not the whole picture yet. Okay, so we have the integral from -3 to 1 of x to the -2. So again, after you apply your power rule, the dx goes away. And if you think about this function, it's really like the integral from -3 to 1 of 1 over x squared dx. And what do we know about the interval from -3 to 1 and x squared? Yeah, there's an infinite discontinuity. So because there is a vertical asymptote, exactly, it's not continuous, therefore not integratable. And I have an example for you because I think we fell into a trap where we thought or assumed all discontinuity implies non-integration. So functions that are continuous segments can be integrated. Functions with discontinuity that's infinite like this one where it's increasing or decreasing without bounds, are a little bit different. So this we can't ever find a value for, but something like this, where you have two functions meeting at a point, well, this could be a quarter circle, and that could be a triangle. That is integratable. Or if you have a piecewise that jumps, so you could find the triangle and the rectangle and sum their areas together. And that was something that I noticed was confusing us. So this is not integratable because you have a vertical asymptote and it's decreasing without bounds. But yet something like this, even though you have discontinuity, because the discontinuity is not on my interval, you can integrate it. So we have 5x to the negative 3 over negative 3 from 3 to 1. And then you plug it in. So you have 5 over negative 3, 3 cubed, minus 5 over negative 3, 1 cubed. So 3 cubed is 27. 27 times 3 is 81. So you get negative 5 over 81. A negative times a negative is a positive 5 over 3. So we could technically multiply that by 27 over 27 to get a common denominator. And we get 130 over 27. Oh, yeah, sorry, thank you. And then my final would be 130 over 81. Thank you. All right. So that's the old. Now we're going to look at the new. So how does the fundamental theorem of calculus change what we're doing? Well, now we might be given these initial conditions, and we have to apply those initial conditions to our areas under the curve. So you're going to be given a statement that reads very similar to that next example. It's going to say, here is our function as a graph. Our graph consists of two segments where we have lines and quarter circles. The function g of x can be represented by the integral that always starts at 0 and integrates the function f of t. Find the values indicated for g. So let's start with the very beginning. If we want to find g of 0 in terms of this problem, g of 0, according to our thing, is equal to the integral. It starts at 0. Our x, or value we're looking for, is 0. So we want to find the integral from 0 to 0 of f of t dt. Well, any integral with the same upper and lower bound is 0. So the integral from 0 to 0 of f of t dt is 0. Therefore, g of 0 is 0. G of 1 would be the integral from 0 to 1 of f of t dt. So f is the graph. 0 to 1 would be this area under the curve on that graph, which is represented by a triangle. So g of 1 would be equal to 1/2 base times height, which is 1. G of 2 would be the integral from 0 to 2 of f of t dt. And now you have two ways of thinking of that. You could think of it as going from 0 to 2, and you could create a trapezoid. You could also consider turning it into two integrals where you integrate from 0 to 1 and then 1 to 2. And we already know the value from 0 to 1 is 1. So now you just have to add to it the value of the rectangle, which would have base 1 and height 2, which is 2. So you get a total area of 3. So what that means is g of 0 is 0, g of 1 is 1, g of 2 is 3. Those represent points on the graph of g. So like at the very end of that activity in that sketch area, those points from I2, and I3 are going to be points on that curve, like plotted points exactly as is. So g of 4 would go from 0 to 4 of f of t dt. So again, what I would do is say, okay, I already know the integral from 0 to 2 is 3. So this is really like 3 plus the integral from 2 to 4 of f of t dt. So that 3 represents g of 2. So that's kind of like saying g of 2 plus integrating 2 to 4 of f of t dt. Initial condition plus your new net change. So this area from 2 to 4 is a quarter circle. That area from 2 to 4 is a quarter circle. So it's 3 plus 1/4 pi. The radius, since it goes from 2 to 4, means my radius is 2. So 4 times 1/4 is 1. So g of 4 is 3 plus pi, which is approximately 6.14. Okay, g of 6. G of 6 would be represented by the integral from 0 to 6 of f of t dt. But again, we already know 0 to 4. So I would think of g of 6 like the integral of 0 to 4, which we just calculated to be 3 plus pi, plus the integral from 4 to 6 of f of t dt. So use what you know to find what you don't know. Use what you know to find what you don't know. So now this is also a quarter circle of radius 2. So if the yellow is a quarter circle of radius 2 and the green is a quarter circle of radius 2, what happens to the integral from 2 to 4 and the integral from 4 to 6? Yeah, so if the upper is equal to pi and the lower is equal to pi, what happens to our pi's? Yeah, so then that means that this integral of g of 6 would be equal to 3 plus pi minus pi, or simply 3. Because the upper area and the lower area of quarter circles with the same radius will cancel each other out. That also tells you something about your original graph. If the upper and lower areas cancel each other out, that means the function of g of x is going to be symmetric from 2 to 6. If the area under the curve from 2 to 4 and 4 to 6 cancel each other, that means the graph we're going to sketch from 2 to 4 and 4 to 6 should have symmetry to create that curve that's symmetric with the areas under it. Does that make sense as to why that's going to occur when we sketch our graph? Okay, I got some head notes. Okay, for VI, VII, and VIII, be very careful. These are no longer asking me about g of x. They're asking me about g prime of x. So let's talk about how the derivative would relate to g. So I'm just going to kind of write on my space. You can use that space in B. You can use this space up above. So up here, g prime of x would be the derivative of the integral of x. Well, what do you know about the derivative and the integral? What did we say they are? What's 1/2 times 2? What are those two numbers called? 1/2 and 2 are blank of each other. Here, reciprocals or another. So now let's say we work that out a little further. And what? Yeah, they cancel out. Natural log of x and e of x are what type of functions with each other? If you do function composition and you have f of g of x equals x, you get your identity. But when you compose two functions together and they equal x, those two functions are, inverses. So natural log of x and e of x are inverses. An inverse is a canceling out method in mathematics. So we actually call 1/2 and 2 multiplicative inverses. It's just for some reason, way back in the elementary days, you guys were taught it as reciprocals, and you can never get that word out of your head. But truly, -3 and 3 are additive inverses when half and 2 are multiplicative inverses. So in calc, the derivative in the integral are inverses. They're canceling properties. So if I take the derivative of the integral, both with respect to x, that cancels. So what does that tell me? G prime of x is really the graph, or f of t. So what that means is if I want to find g prime of 1, it's the value on the curve. So g prime of 1 is 2. On Monday, we're going to talk about algebraically exactly how that works. So we're going to actually take the integral, then take the derivative to show you specifically how that works, because that is a representation of part 1 of the fundamental theorem. So g prime of 4 would then be 0. And g prime of 6, I don't know why my board keeps turning on, would become -2. We use those second derivative and derivative values for part B to help me sketch that curve, because if I know the sign of a derivative, then that allows me to know what was happening on that function. So for example, if the derivative of a function is at 0, that means on g of x, at x equals 4, what do I have? Yeah, this is an extrema. Excellent. And if it's negative to the left of the extrema, that represents decreasing. And if it's positive to the right of the extrema, that represents increasing. So if the derivative is increasing and then decreasing, my extrema will be a max. So take the answers you've got through I through B, or 1 through 5, and plot each of those points on your next graph. So take those answers and plot each of those points on your graph. So if you think about what we just said, we said at 1, it was increasing. So that would make sense here. At 2, it is, we didn't talk about it, but we could. At 2, that value is at 2. So also positive, so increasing. And then at 4, it's at 0. So we can almost see my extrema happening at 4. So if you went back and you talked about that original graph, if the original graph of f represents g prime, if the graph of f represents g prime, if G prime is decreasing, then my original graph will be concave down. And you can see from 2 to 6 on F, it's decreasing, hence my graph being concave down. From 1 to 1, the graph is increasing. So that means that from 1 to 1 on this curve, I need to show concave up. Now from 1 to 2, my graph is a constant. The derivative of a constant becomes a 0. So if you take the antiderivative of a constant, you would get something linear. So that means on my graph of G, I need to show a line from 1 to 2. Because if you have a constant, think about the antiderivative of a constant would be a line. The antiderivative of a constant would be a line. So we should have a line from 1 to 2. Okay, in example 2, it says use a graph of f prime to find f. So again, we have a semicircle and a line segment. So if I want to find f of -4, I want to find the value of the area under the curve. So I could do that one of two ways. I could do that algebraically by making that a circle and subtracting the rectangle from it. So again, it would be a full rectangle, and then you'd subtract the circle to get the blue. And then we are given, and this is where it's coming into play, the initial condition that f of 0 equals -3. That matters now. So think about in terms of our net change. It's the integral from a to b of f of x dx equal to f of b minus f of a. So in this case, my f of b is -4. So what we're going to do is take that f of a, which is 0, and kind of add it to this. So this is the integral from -4 to 0 of f prime of x dx, which says that equals f of 0 minus f of -4. Sorry, I can't read. So the integral represents the area under the curve, so that's the area of a rectangle. So the rectangle has width 4 and height 2. Minus the area of a circle. So it's a half circle, which is 1/2 pi. The radius is 2. So the left part of this equation is rectangle minus circle divided by 2, since it's only the bottom half. So you get 8 minus 2 pi. And that equals f of 0, which was given to me, minus f of -4. So I can use that to solve for f of -4, which is what I was being asked for. This problem is different from the example above, because in the example above, g of 0 was 0. Now, f of 0 is not 0, so that's my initial condition. So now you have to apply the fundamental theorem of calc. So we're going to add 3 to the other side, leaving me with negative f of 4. So I have to divide everything by negative 1. So 8 plus 3 is 11. 11 divided by negative 1 is negative 11. Negative 2 pi divided by negative 1 is 2 pi. So f of negative 4 is equal to negative 11 plus 2 pi. Because essentially we took our initial condition and worked backwards from it to find the value of the function. Okay, let's look at f of 3. So again, f of 3 would be like the integral from 0 to 3 of f prime x dx, which would equal f of 3 minus f of 0. So the integral from 0 to 3 would be this triangular area above and that triangular area below. So the integral would be the upper area, which is 2, minus the lower area, which is 1/2. So that makes the total area or net change from 0 to 3, 3/2. And then taking into account f of 3 minus my initial condition of negative 3, which is kind of like a plus 3. So now you have f of 3 plus 3 minus 3. So you're going to subtract 3 from 3/2. So f of 3 is equal to 3/2 minus 3, or negative 3/2. So what that means is f of negative 4 is 2 pi minus 11. F of 0 is negative 3, and f of 3 is negative 1.5. So you could kind of get your graph of f plotting those points. So take a minute, go take your 4 minutes, come back around 9:27, stretch out your legs, and then we'll pick up with one more graphical example and the rate in and rate out example.
Can you watch my egg?
What? Did you say you're going to eat his egg? Yes. See over there? Only person asked. They're so mad at me yesterday. See, Zach left his again. Like, no lesson left. He came back. I was just going to steal him. Where's Mrs. Young? She'll come take him. See, that makes me stare. get to the bathroom. I had to babysit last year. The eggs were in the fall. They were during the senior assembly. So, like, I had a baby egg and Mrs. Volanich had a baby egg during like your senior assembly.
My baby is literally like me and my egg went to work again. My egg got work.
We walk around the parking lot again.
When the weather perks up.
It's not that bad.
Today maybe, but
I don't think they even I don't know, they had them last year.
We don't really need it, but like, it's nice to have. We're standing in the lobby.
okay. So, in example number 3, use a graph of f prime to find the absolute extrema. Let f be a function defined on the closed interval from -6 to 6. Again, initial condition is given at 0 equals 3. And our graph consists of 4 line segments. Hope if I could type. And 1 semicircle as shown below. So, again, 4 line segments, 1 semicircle, and initial condition that at f of 0 on the original, it's 3. So again, this is the graph of f prime. We're looking for values related to the original. Okay. Could you look at yes. So that would help you understand, like, knowing where the graph is going left or right. But that wouldn't help you find the area. Are you asking for, like, this first question where I say, like, we must first find f prime when it equals 0? Okay, yeah, which is, yes. I thought you were asking me, like, a general question. I was very confused. I was like, what? Yes. So, yes, the zeros of the derivative will represent the maximums or minimums of the original. So, your question number 1 is, how do we find them? And you're exactly right. We are going to find the zeros of f prime. So to find the absolute max value, we're going to start by finding the zeros of the graph of the derivative. So first we find when f prime equals 0, and that is at -4, -2, 2, and 5. Now, the problem with that is that we also need to consider our endpoints, because endpoints can also represent extrema. So the zeros of the derivative are -4, -2, 2, and 5. And then we also need to consider the endpoints, which are -6 and 6. So what we're going to do is what we call that candidates test. We did this for EVT back in section 1. So what you do is you find the x values at each of those key points. So we're going to find like -6, -4, -2, +2, 5, and 6. And that initial condition comes into play because now to find -6, it's the area under the curve from -6 to 0. So I'm just showing you like the candidate test for either. And we're going to find them only because they're going to be a change in positive to negative area. So like to get -6, we need -6 to 0. But when you're looking at your graph, and it's going to have some weird numbers on it right now, you would break this down into the integral from -6 to -4 to find this area. 4 to -2 to find that area. And then you're going to do the quarter circle or find the total area and cut it in half. So you kind of have a few choices. You can label your whole graph. And then the reason I do the candidates test, even though I know their minimums at -4 and 2, would simply just to be able to find the function value at those points. So you have a choice. If you want to find all your areas on the graph and label it, you can. So think about the area of this triangle here. Base 2, height 1. So 1/2 base times height makes an area of 1. Here, base 2, height 2 gives an area of 2, but it's below the curve. So we have to make sure when we use that as an integral, we use it as a negative. Radius 2. So that means the half circle is pi r squared, where r is 2. So it's 2 squared, which is 4 divided by 2. So this has an area of 2 pi. Here, base 1, 2, 3, height 2. So 1/2 base times height makes this area 3. And down here, 1 and 1. So that's 1/2, 1, 1. So that makes this area -1/2. So when you go over and you do your candidates test, all of these function points are going to matter because they're going to be your initial conditions. So I actually start my candidates test more in the middle because I'm going to find the area from -2 to 0. So the integral from -2 to 0 of f prime x dx is equal to half of 2 pi, so that's -pi. But then I need to take into account the initial condition. So So f of negative 2 is equal to f of 0 and subtracting that negative pi. So it becomes 3 plus pi. And if you want to see that worked out, again, what we're saying is the integral from 0 to negative 2 to 0 is equal to f of 0 minus f of negative 2, where f of 0 is given to you as 3. This area is given to you as negative pi. So f of negative 2 would become 3 plus pi, because you'd subtract the 3 over and divide by your negative 1. So the reason I do the f of negative 4 and positive 2 in my candidates test isn't really because I actually think they're extrema. It's because I need them to help me find the values for those integrals. So the integral here would be negative 4 to 0 of f prime t dt equals f of 0 minus f of negative 4. So we said that the area from negative 2 to 0 was negative pi. And then the area from negative 4 to 2 is positive 1. So that's like 1 minus pi for the left side. Equals f of 0, which is 3, minus f of negative 4. So subtract over your 3. 1 minus 3 is negative 2. Divide by negative 1, and we get f of negative 4 equals positive 2 plus pi. So you could do negative 6, and I'm going to change it up a little bit, to negative 4 instead of to 0. Because we know f of negative 4 from my previously calculated step. So the area under the curve from negative 6 to negative 4 we said was negative 2. So that makes the integral value negative 2. We said the value of f of negative 4 was 2 plus pi minus f of negative 6. So subtract 2, you get negative 4. And then subtract pi, you get negative pi. Divide by that negative 1. And we get f of negative 6 is 4 plus pi. So do you see how you don't have to always make your bound with respect to that initial? Once I find another value, then I can use that value to find an area under the curve where you break it up into the segments that are changing. So 2 would be the integral from 0 to 2 of f prime t dt equals f of 2 minus f of 0. So we said the area of that quarter circle was equal to pi. F of 2 is what we're looking for. F of 0 is 3. So add that over, and f of 2 equals 3 plus pi as well. So again, we see that symmetry with the semicircle in the graph and with our values on the function. At 5, again, you could go on your integral from 2 to 5 of f prime t dt and say that that's equal to f of 5 minus f of 2. And the area from 2 to 5, we said was 3. F of 5 is what we're looking for. And f of 2 is 3 plus pi. So you'd add your 3 over, and you'd get 6 plus pi. Yeah, so the negative here would distribute. And then at 6. So again, you have two ways if you want to think about it. For 6, you could go from 0 to 6 and have to sum up all your areas. Or you could go from 5 to 6. And we know that that area under is negative a half. We're looking for f of 6. And f of 5 would be 6 plus pi. So then that would be negative 6 and negative pi. So when you add it over to the other side, it would become positive 6 minus a half, which would be 5.5, and then plus pi. So it should make sense that the value from f of 5 to f of 6 only changes by a half, because your area under your curve is a half. Does that make sense in terms of the points on the graph? Can you see how like the area directly relates to each of those values? Okay, we'll save, so it actually means we're going to put Fundamental Theorem Part 2 to half of Monday along with the rates of change, because those are really important. And I think they're going to take us, each one's probably going to take us about 10 to 15 minutes based on that timing. So I did create, our textbook problems for Fundamental Theorem aren't great. So I have some worksheets for you. And I'll pass that packet out now. And due to the fact that we're not doing rates in, rates out, and I want to pass back your chapter tests, we're going to do that for the last little bit of class today. Because we're adjusting for not doing the word problems, is going to be, let me more or less look at it. There you're doing number 1. I might be adjusting this even too. So I might be sending you a textbook problems because I'm changing for lesson. You're definitely doing problem 1 on this though. When you get to your row, we pass whenever to go. Okay, so you're going to do problem 1 on that packet, and then I'm going to give you either a different worksheet that I have or some textbook problems, because the rest of them all you need the skill sets that we're going to get from doing the rate in, rate out notes. So I don't want to give you those problems yet. We're me open up our book. Okay, so fundamental theorems on page 302. I'll print you off the secondary worksheet. And while I do that, I'll let you look at your chapter tests, and then we'll go over any questions, comments, concerns you have for them. So in order to go over your chapter tests, I need you to put all devices and writing utensils away. So what I did was took my score. I actually gave you a per. So your score in here versus what's in Skyward doesn't match the bottom number. No, like what's in Skyward is staying what's in Skyward. What I'm saying is like the base number in Skyward is after I looked at like all of the scores in purple. So typically with this test, since it's like a midterm, I kind of put a curve on it because I know it's a lot of material. Chapter 4 was the last part of derivatives. So I'm saying is the highest score was a 145. On Skyward, it's at 145. All right, so let's talk through it. Talk about any questions, comments. I'll let you look through, and then I'll go over what I thought were issues, and then we will, go from there.